Alright, so we have been talking about solving a system of equations by graphing, and so far we've just looked at it on a calculator. And we saw what is going on in this next slide here, is that when I'm solving a system of linear equations, I'm basically looking for where the two lines intersect each other. I am looking for the point of intersection. So that's the key interpretation here. When I'm solving a system of equations, each equation is a graph, and the solution is the point or points where they intersect each other. Okay? The points that they have in common. So, this is the simplest way to solve a system of equations. The simplest way to solve a system of equations. Step one is that you just graph each of the equations. If they're lines, piece of cake, right? So I just graph each one of the lines, and then step two, I'm just seeing where those two lines intersect each other. I'm finding that point of intersection. So as you can see here from the picture, I have these two blue lines, each one graphed, and the solution is the point of intersection there, which is 3, -4. So let's actually try this ourselves, right? So we're going to graph this linear system and then find the point of intersection by graphing them, right? So I have both of these equations in standard form. Let's see if we can put them in slope-intercept form, basically in our head. So just one step, I'm solving these things for one. I'm going to do this right up above here. So this top equation, what I would have to do is I would have to subtract the 5x over, so it's going to be negative, and then I'm going to divide everything by -2. Okay? So the top equation is, I'm going to subtract over the 5, so it's negative, but I'm dividing it by -2, so it's going to be positive. So 5 halves x. Then I have -10, and I'm going to divide it by -2. That's going to make it a positive 5. Okay? If you have trouble doing it like that, then just do it step by step on your paper. Okay? Let's try it again on the bottom equation there. Again, I would move the 2x over here. It's positive. I would subtract it over, so it's going to be negative. I'm going to divide it by -4, so then it's going to become positive again. So y is equal to, subtract it, I have -2, divided by -4 is positive 1/2 x. And then I have positive 12 divided by -4 is -3. And again, if you had trouble following that, doing it in your head, just do it step by step on your paper. Okay? Okay. So let's graph the top equation. It's starting at a y-intercept of 5 there. And I have a slope of up 5 and over 2. So up 5 and right 2. Or maybe I could have gone down 5 and left 2. I'm just going to go ahead and get a couple of more points here. And let's see, 2 and 2. Maybe your graphing skills, especially with a ruler, are superior to mine. Or maybe they're not. Okay, the next one is starting at -3 on the y-axis, so start here at -3, and my slope is 1/2. So I'm going to go up 1 and right 2, and I can see that I'm not going to touch the other line going in that direction, so let's go in the other direction. Down 1, left 2, down 1, left 2, and I just found the point of intersection. Down 1, left 2, just to get a nice sweet line there. Let's change the color. Boop, boop. Right there. I'm going to mark that point of intersection there. Let's see what the coordinates are. We've got -4, -5. -4, -5. Okay? This is supposed to be the solution. And the second part is check this thing algebraically, which just means put it into each of the equations and make sure that it works in both equations. So let's put it in the top equation here. And I don't care if you put it into these or you put it into the y equals form, makes no difference. So let's put -4 in for x in the top equation. 5 halves times -4. 5 halves times -4 plus 5. Let's see what that equals. So 5 halves times -4, so this will go in there -2 times. That's -10 plus 5, which is -5. That one checks out. Okay, let's do it in the bottom equation. 1/2 times -4. No, whoops. Whoops, mixing it up with the top equation, minus 3. Okay, so this 2 will go in negative 2 times. So I have negative 2 minus 3, which is also negative 5, and I can see it checks out. All right, so that's all you have to do. Graph each one of the equations, find where they intersect, and then it's always a good idea to go back and check to see if it actually works in the original equations. All right, so I have a follow-up question for you. What do you think is the limitation of solving a system of equations by graphing? Sure, it's a simple method. I just graph each one of the equations and see where they intersect. What do you think the limitation of doing it by this method is? So take a second, think about it. What do you think? Well, if I go back to this previous example right here, it was fortunate that the answer turned out to be on exact grid marks. But what if when I go to graph these things, they turn out to be on non-integer grid marks? They don't intersect at exact integers. Then I'd have to approximate where that is, and it's kind of a headache. In that case, a different method would probably be better. Maybe substitution and maybe elimination, and that's what the next lesson is going to be about. So, I want you to try to do these on your own. Solve each of these by graphing, and see what the point of intersection is. You got two systems there. So pause the video and okay, so let's see what you came up with. So on the first one, I went ahead and solved for y on both of the equations. The top one, it was pretty easy, just y equals negative 3/2 x minus 2. Graph that equation. The second one was a little trickier because its y-intercept was a third. So what I did instead is I started at the x-intercept. If I plug in 0 into that second equation there for y, I'd have x equals 1. So instead I started with the x-intercept and then used the slope of negative a third and saw that their point of intersection is negative 2, negative 1. So there's the solution to that system of equations. Over here on number 2, same kind of thing. Solve each one of these things for y, just easier to graph. Find a y-intercept and a slope. Same thing on the second one, and I get a point of intersection of 0, negative 8. Now, if I looked at the equations there, maybe I could have seen, maybe I could have seen that they both share the same y-intercept, and I would have known without graphing it that that's what the point of intersection would have to be, since they have different slopes. Okay, so on these next two that I want you to graph, to solve the system of equations by graphing, a couple of tricky things would happen, and so I want you to see it for yourself right here. So graph each of these systems of equations and find out what the solution is, the point of intersection. Alright, so did you see the two tricky things that sometimes happen when you're solving a system of equations? Let's look here. So on the first one, whenever you go to put it in y equals form, it turns out that you have the exact same equation. The first equation is just, or the first equation is a multiple of the second one, or vice versa. Okay, so whenever you graph it, you only have one line. The other line would be exactly on top of it, and so they intersect everywhere. They intersect everywhere. There are infinitely many solutions. Okay? One of the solutions is just any point that's on the line. For example, this point at 3, 0 satisfies both equations. That's one of infinitely many solutions to that system of equations. Okay, look at number 2 here. Whenever you go to solve for y on each of these, you end up with the same slope. So when you graph them, they're parallel. If they're parallel, they will never ever intersect each other. If they never intersect, there's no point intersection. This means that there's no solution. There's no point from the top equation that's going to also satisfy the bottom equation. So here's what I should expect to happen whenever I'm solving a system of equations, by graphing or by any method. So the first one is what we did right over here, and that is nothing strange happens. I graph the lines, I find one point of intersection, and that's my solution. Okay? The other two strange things that might happen is whenever I go to graph them or solve them, first it might be the same exact equation, in which case there's infinitely many solutions. And then lastly, whenever I go to graph them, I see that they are parallel to each other, so they have no solution in common, and I would write no solution. Now, in the next video, we're going to classify each one of these cases with some special terminology.